Okay, with this video I'd like to finish up the discussion and exposition of the FIR design by windowing technique. And we've spent a few days on this and now have gotten through an initial example. And so what I'd like to accomplish now is to review that example and then see some of the different ways that we can modify the technique to adapt to the particular situation we have and see what other options we have for how to complete this technique. So let's back up a little bit first and review the example that we did at the end of class, which was starting with a low-pass filter and converting it to a high-pass filter. And so the specifications we were given were that we wanted a high-pass filter, and it was going to operate at a sampling frequency of 10 kilohertz. The passband edge for the high-pass filter was supposed to be at 0.4 cycles per sample. That's the beginning of the passband at high frequencies. And the edge of the low frequency stop band was at 0.15 cycles per sample. That meant we would have a basic shape for our magnitude response that we're trying to achieve, with the stop band at low frequencies, the pass band at high frequencies, and F, the stop band edge at 0.15, pass band edge at 0.4. The specifications for how good the pass and stop band had to be has a minimum stop band attenuation of at least 40 dB and a maximum pass band attenuation of 1 dB. And so we've got our filter specifications, and in this case we're going to start by using a low-pass filter prototype that will design the low-pass filter and then transform it into a high-pass filter. Now this is one of two options for how to do this technique, and it's the more typical approach. So we'll use that as our first illustration. If we're going to start with a low-pass filter, though, we have to tailor the design specs that we have for the high-pass filter for the low-pass prototype. And so the difference is the frequencies that are part of the stop band of the high-pass filter are actually part of the pass band of the low-pass filter, and vice versa. The pass band of the high-pass filter is the stop band of the low-pass filter. So we have to exchange the specifications here a little bit. That means for our low-pass filter prototype, the stop band edge frequency is 0.4 and the pass band edge frequency is 0.15. And the difference between them, which we call the transition width, that's the delta ft, is the difference between 0.4 and 0.15 or 0.25 cycles per sample. All right, now that we've reestablished what our specifications are and how they apply to the low-pass prototype, we need to choose our cutoff frequency. Now, in the particular transformation that we're going to use to convert this low-pass prototype filter to a high-pass filter, the high-pass filter we create has the same cutoff frequency as the low-pass filter. And so we should choose the low-pass filter's cutoff frequency to be where we want it in the high-pass filter. In our typical case, that'll be halfway between the pass band and stop band edge frequencies. So with a pass band and stop band edges at 0.4 and 0.15, we average those to find 0.275 to be the frequency we want to use for the cutoff. Now this is a parameter that we need, that we're going to plug in to the impulse response for the low-pass filter, so we need to determine this ahead of time. So we've got our low-pass prototype. We know what its impulse response is. It's an ideal filter, so the impulse response is a sinc function. And now we get to choose the window function that we're going to use to take the truncated impulse response for an ideal filter and tailor it, shape it so that it has better frequency characteristics. So we want to choose a window based on the stop band attenuation or the pass band attenuation or the ripple requirements, which are just different ways of expressing the same issues. With our 40 dB stop band requirement, we go into our window function design table and try to find a window function that has at least 40 dB of attenuation for the stop band. And looks like the von Hann or Hanning window will be sufficient for that. A Hamming window would also work, but it's a bit of overkill, and the Hamming window would result in a longer filter as we try to tweak in the transition width. So we want to choose the window function that has at least the minimum amount of attenuation we need, but not a whole lot more. Now we need to also verify that the passband attenuation requirements will be met. The handing window is good for 1/10 of a decibel of passband attenuation, maximum attenuation. We're allowed 1 dB, so this window function will be fine. Now that we've chosen our window function to achieve the attenuations we need, now we need to adjust the filter length, the filter order, in order to achieve the transition width we need. That's what we had chosen before. We had computed the transition width, so the difference between the passband edge frequency and the stopband edge frequency. For this particular filter, the relationship between the transition width and the filter length is this constant C that has a value of 3.21, and C is, we use that to compute then what the length M is that we need to achieve a certain transition width. And by the equation, the transition width is given by the ratio of this C constant over the length of the filter. So solving for the length of the filter, we need to divide the 3.21 C value from the table by the allowed transition width for our filter, which was 0.25 cycles per sample, and that gives us a 12.8 as the length we need. We need an odd length filter to create a type 1 linear phase FIR filter, so we'll round this up to 13. And that'll be our first attempt. So our design choices then, we've got our cutoff frequency, we've got our window shape, we've got our filter length of 13 now. Now it's a matter of just doing the computations to figure out what is the impulse response of this 13 length filter using this window, and then analyzing to make sure it meets all our specs. We plug in to the sync function, the ideal low-pass filter's sync function impulse response, sine 2 pi fcn over pi n, and plug in for different values of n. For a 13 length filter, if we use n values that are centered on 0, we would go from n equals -6 to n equals +6 in this sync function, and get those values for the ideal low-pass filter's impulse response. We're going to multiply that by the handing window function, which is given by 1/2 of the quantity 1 plus cosine 2 pi n over m minus 1, using m equals 13, plugging in again n values from -6 to +6. We get this collection of 13 sample values for the window function. Multiplying those two together, the window function sample values by the impulse response sample values, we get the windowed low-pass filter impulse response for our filter that we're designing. Time to analyze those, see what results we got, and this is where we ended up last time. We saw that indeed running that filter through our MATLAB analysis program and getting a frequency response at the defined passband edge frequency for our low-pass filter of 0.15, we had only 0.1 dB of attenuation, which is well within the 1 dB spec. At the stop band, we needed 40 dB. We have 39.9, so this looks like pretty much a sufficient filter. Now, if we were designing a low-pass filter, if this was really what we wanted and we're trying to meet these specs exactly, we might want to prove this a little bit to try to bring that stop band attenuation up a little bit more. And we'd also want to explore whether or not we could actually achieve these specifications with a shorter length filter. Particularly since we have much better performance in the passband than we need, we might be able to compromise a little bit on that in order to achieve still the stop band characteristics we need. And so something we might explore is seeing if we could actually achieve meet all our specifications with a slightly shorter filter. In this case, again, we want to maintain an odd length, and so our next ratchet down from 13 would be an 11 length filter. And so, okay, we might try that, m equals 11, and we might also notice that we could help ourselves a little bit by moving down the cutoff frequency, because when we make the filter shorter, we're going to actually make the transition region worse which without any other change might compromise the attenuation we're achieving at the stop band edge. And so if we've got some characteristic like this with our m equals 13 filter, we can assume that with a shorter filter like m equals 11, that transition width is going to be a bit worse. And we won't have as much attenuation at the stop band edge as we achieve with the longer filter. So to fix that, we might consider moving things over a smidge. So if we try the m equals 11 filter, we need to do something else, and that's moving the cutoff frequency just a little bit. And the question is which way, left or right? And so as you might surmise, because of the way the diagram was following the frequency response and we had just barely enough attenuation in the stop band as it was, we might want to move that cutoff frequency down a little bit. The idea being if we're just barely making it, as we appear to be here, if I can move this whole curve down a little bit by shifting down the cutoff frequency, I'll get a better attenuation in the stop band while giving up a little bit of getting more attenuation in the pass band. But since I have some room to spare there, I think it's going to be safe. So the idea is to shift that whole thing down by changing the cutoff frequency target. So let's give that a try. And so dropping the cutoff frequency to 0.245 and using an 11 length filter, we follow the same process. We use a capital M equals 11. N values now go from -5 to +5 instead of -6 to +6 for both the ideal impulse response and the Hanning window. Multiplying those together, we get this impulse response for the windowed filter. Plug that into MATLAB and see what we get. In this case, if we were designing a low-pass filter to meet these specs, we have indeed achieved them. We have just barely enough attenuation in the pass band to stay within the boundaries of the maximum allowed, and now we have a little bit beyond the specified minimum for the stop band with a shorter filter, and shorter again translates into less expensive. And so if we were designing a low-pass filter, this would have been a successful design. Probably about as short as we can make it and still meet all the specs. Unfortunately, we weren't designing a low-pass filter. We were originally intending to design a high-pass filter that met these specs. And so if we go through the transformation to turn this low-pass prototype into a high-pass filter, well, we have different transformations depending on what we're transforming to, a high-pass, band stop. This particular one that we're going to apply to turn a low-pass filter into a high-pass follows the idea that the low-pass and high-pass frequency responses look like one is flipped over relative to the other. Or in other words of saying that the frequency response of the high-pass filter looks like 1 minus the frequency response of the low-pass filter at all frequencies, assuming both have pass bands gains of 1. If we take the inverse discrete time Fourier transform of that relationship, we can get the time domain equivalent of how we do that transformation when we operate on impulse responses instead of frequency responses. In this case, to convert a low-pass filter's impulse response into a high-pass filter's, we're going to follow that minus sign. That means we're going to change the sign of all the sample values in the windowed low-pass filter impulse response. And adding the delta sub n function means we're going to add just a 1 to the center sample of the impulse response, the peak sample there, and zeros to all the other samples. So only to the one sample will we add that extra value of 1. Looking at that numerically, here's the sample values for our low-pass filter impulse response, where we have the first value here, the center value here, and the last value over here. And again, we have the symmetry that we expect, the even symmetry around the center point. To convert this to a high-pass filter with the same cutoff frequency, we're going to change the sign of all these different values and then add a 1 to just the center sample. So doing that changes the minus 0.001 to plus 0.001. The minus 0.0365 becomes plus 0.0365. Also the center sample, the plus 0.49 in the center becomes minus 0.49. When we add 1 to that, we get a positive 0.51. So that's where we have this adding 1. We do that after we change the sign. And all the other values have their signs changed relative to the low pass. So notice that the low pass filter has a sinc function style impulse response. The high pass filter has this characteristic positive surrounded by 2 negatives and then some more tails on the end. Now if we were to analyze the frequency response of our filter, the low pass version of this filter with a length of 5 and cutoff frequency of 0.245 looked like this. Looked like it met all the specs. But when we do look at the high pass filter version and find the frequency response of this function, we see that, well, in the pass band, at the pass band edge, we did meet the requirements of staying within 1 dB of attenuation. But now at the stop band edge, at 0.15 cycles per sample, we don't have minus 40 dB, but we have minus 20 dB, or minus actually 19.6. So why is that when our window we chose had attenuations that should have been more like 40? No, this was the fallacy of the adjustment that we made trying to improve our low pass filter. By improving the low pass filter, we actually degraded the transformed high pass filter. Because remember, the low pass filter's pass band relates to the high pass filter's stop band. When we shortened our low pass filter and tried to improve its attenuation, we were improving the attenuation in its stop band. Well, that was improving the high pass filter's pass band. We did it by compromising on the attenuation in the low pass filter's pass band, which resulted in compromising the high pass filter's stop band. So the moral of the story is, as we tweak in our designs, we really need to be careful and be cognizant of what's the final filter that we're trying to achieve, not the intermediate prototype filter. And we should be manipulating that final design, not the intermediate one. So here, the high pass filter's stringent stop band requirements have to actually relate to the low pass filter's pass band. Now, how do we do that? These attenuation allowances are very different. And so if we really want to compare things and match things up, what we would actually want to do is look at the ripple specs, not the attenuation specs. In the case of the low pass filter, if we translate this 40 dB of attenuation to a ripple value using our equations, we find that it's an allowed amount of ripple of 0.01 in the pass band of the low pass filter, which is the stop band of the high pass filter. And similarly, the 1 dB attenuation for the stop band of the low pass filter becomes a 0.0575 amount of ripple in linear terms in the pass band of the high pass filter or the stop band of the low pass filter. So these are the specs that we should be paying attention to if we're looking at the ripple amounts at the intermediate filter. So it turned out our original design that had a length of 13 and a target cutoff frequency of 0.275 and had these results in the low pass prototype, which just barely met the specs or appeared to, had actual ripple amounts that were pretty close to what we needed. So if we looked at the ripple specs based on the attenuations that were allowed, we had a maximum stop band ripple allowed of 0.0575 and a pass band ripple of less than 0.01. And we see we had about 0.01 on both sides here. And so this filter was almost adequate for achieving both. Didn't quite achieve this ripple amount that we needed here. And when we do the conversion, we could see that that would be the case. So converting this to a high-pass filter, taking the low-pass prototype, transforming it into a high-pass filter, and analyzing it, we see that we, in fact, did meet the spec on the pass band of the high-pass filter, but we were just a little bit shy on the performance we needed in the stop band at the stop band edge. Now, looking at this design, rather than the low-pass filters, we probably would not want to shorten this necessarily. We probably would want to at least adjust the cutoff frequency a bit to again slide this whole response over a little bit to make the stop band better, give us more attenuation there, while we give up a little bit in the pass band. And so we can do that if we change the cutoff frequency up to about 0.28 and redo the design, still with the handing window and still with a length of 13. Now our prototype low-pass filter would have this impulse response shown. We would invert all the values, change their signs, add one to the center sample, and we would come up with these transformed values for the high-pass filter's impulse response. And that results in this filter, which meets all of the specs. So now we have a passband attenuation of only 0.14 dB. We're allowed 1 dB, and here we're exceeding the 40 dB mark at the stop band edge by about 3 dB. So seeing that we're exceeding the specs now with this filter, having adjusted the cutoff frequency, now we could look at, well, could we now make this work with an 11 length filter? And again, after a few iterations and playing with it, we'd have to again adjust the cutoff frequency, but it turns out that taking the cutoff frequency of 0.305, using a filter length of 11 and maintaining the handing window, and coming up with the windowed impulse response values for the low pass filter, transforming it to a high pass filter. Success. And so that's how this design would typically run. It's again, we use tables and things to choose our window function. We set our cutoff frequency based on the pass band and stop band edge frequencies. We adjust the filter length to get the transition widths we need, and usually the technique itself will give you a design that's pretty close. And we have to either play with it a little bit to make it a little bit better, or explore whether we could achieve the same results with a slightly shorter filter through an iterative process. Again, the best way to do that process is to make sure we're looking at the final version of the filter. If it's not the low pass filter, if it's something else that we're designing, we should look at the final version, not the intermediate version. And so again, the process, get the specs, choose our cutoff frequency for our prototype filter, choose the window shape that satisfies the stop band attenuation, the pass band attenuation, and all the ripple requirements. Then adjust the filter length, maintaining an odd length to get the narrow enough transition bandwidth to meet the requirements. And then it's simply computing the shifted and windowed impulse response and doing some analysis on it to see if we achieved what we needed. And then an iterative process of just kind of tweaking it in. And going through transformation if we need to change it to a high pass, band pass, or band stop. Now, how do those other transformations work? So if we work with a low pass prototype, we can indeed convert it not just to a high pass filter, but also to a band pass filter or band stop filter. Again, assuming that you're working with a low pass prototype that has a gain of 1 in the pass band. And all of these transformations are actually spectral transformations that rely on either shifting or modulation properties of the Fourier transform. We've looked at the first transformation, which is converting a low pass to a high pass, and that's based on the idea of taking the magnitude response and flipping it over so that the frequency response is 1 minus the low pass frequency response, and that gave rise to taking the unit sample response for the low pass filter, changing all of its signs, and adding one to the center sample. Now, in this transformation, the cutoff frequency of the low pass filter is the same as the resulting cutoff frequency of the high pass filter. And so we would choose the cutoff frequency for the low pass filter the same way we would choose a midpoint between the pass band edge and stop band edge frequencies. There's a second way to do a transformation from a low pass filter to a high pass filter that works as well, although in this case the high pass filter's cutoff frequency is different from the low pass filters. This is based on the idea that a high pass filter's frequency response actually looks like a shifted version of the low pass filters. So we take a two-sided low pass filter, again looking at the positive and negative frequency ranges, and then shift that over so that now that it's centered on the Nyquist frequency, and make all the spectral replicates of it, we have a high pass filter's characteristic or magnitude response. And so we can create a high pass filter's frequency response by shifting the frequency axis of a low pass filter by the Nyquist rate by minus 0.5. If we inverse transform that relationship, we can use the Fourier transform shifting property, where shifting something over is the same as multiplying it by an exponential. In this case, e to the minus j 2 pi n times the amount of shift, 0.5. So we take the unit sample response of a low pass filter. To transform it into a high pass filter's unit sample response, we would multiply it by this exponential quantity. If we factor out that n from the exponential quantity, we find it's e to the minus j pi, which is actually a value of minus 1. So this is like minus 1 to the n multiplied by the unit sample response as a function of n of the low pass filter. How you implement that is actually multiplying every value of the low pass filter by either 1 or minus 1, depending on the value of n. If n is odd, we multiply it by minus 1. If n is even, we multiply it by 1. Now again, in this case, the target that we have to set for the low pass filter's cutoff frequency in the low pass prototype has to be modified in order to end up in the right place to have the correct cutoff frequency for the high pass filter. In this case, the cutoff frequency of the low pass filter should be set to 0.5, the Nyquist, minus the cutoff frequency desired for the high pass filter. So that has to go into consideration if we're going to use this transform before we compute the impulse response values for the low pass prototype. Similarly, we can take a low pass filter's magnitude response and convert it to a band pass filter's frequency response by using either a shifting or by using a modulation, like amplitude modulation. So if we multiply this frequency response by a cosine function, we'd modulate things. And so the band pass filter's unit sample response is the same as taking a low pass filter's impulse response and modulating it by a cosine with a factor of 2 to account for the fact that usually when we modulate by cosine, we get half the amplitude going up in frequency, half the amplitude going down. And so by multiplying by 2, we maintain the proper amplitude of the frequency response. Looking at what that's doing in the frequency domain, that's just confirming that we would start with a low pass filter's prototype. We would make copies of that centered now at plus f0 and minus f0, where f0 is the center of the pass band of the band pass filter that we're after. Using those relationships, then we again need to choose the cutoff frequency for the low-pass filter's prototype. For the unit sample response values we're going to compute for the low-pass filter based on the values that we want for the center of the pass band of the bandpass filter, which is called F0 here, and the pass band edge frequency and stop band edge frequency for the upper part of the bandpass filter, so F3 and F4. We would compute the cutoff frequency for the low pass filter using this formula, and then design HLP, the low pass filter's impulse response, using that cutoff frequency, use an appropriate window function, and then to transform that low pass to a band pass filter, we would multiply all the unit sample response values by this cosine function and a factor of 2. Similarly, a band stop filter, or an inverted version of a band pass filter, well, we're going to take advantage of that inversion idea again. So we want to flip things over. In the frequency domain, that's like 1 minus. So the band stop filter's frequency response is like 1 minus the band pass filter's frequency response. And we know at the band pass filter's frequency response how that relates to things. So to find the unit sample response of a band stop filter, we would take the unit sample response of a band pass filter, invert all of its sample values, and add 1 to its center. In order to get that bandpass filter's unit sample response, we would start with the high-pass filter's unit sample response and modulate it with the -2 cosine 2 pi nf. So we'd have to do that combination of operations on the prototype filter's unit sample response in order to convert it from a low pass to a band stop. So change all the signs of the band pass filter samples, add 1 to the center, where those band pass samples came from a modulated version of the low pass filter's impulse response. Again, if we want to choose the cutoff frequency for the low pass filter so that after this transformation all the band edges show up in the right places, we would use the formula shown here to convert the band stop filter's notch center frequency and edges to the cutoff frequency of the low pass filter prototype that we're going to use. Okay, taking that all into account, let's see how that would work with the design that we've already used. So here's a bandpass filter with a sampling rate of 10 kilohertz, pass band edges of 0.1 and 0.4, so similar locations, stop band edges at 0.15 and 0.35. That means the center of the pass band is halfway between the F2 and F3 frequencies, or at 0.25. If we want an attenuation of 40 dB and pass band attenuation of 1 dB again, we would design this filter first with a low pass filter. So we want a band pass filter with a 10 kilohertz sampling rate, and these edge frequencies. In order to create them, we would need a low pass filter with a transition width that matched the transition width of the band pass filter that we needed. And so that would be, in this case, 0.15 minus 0.1 or 0.05. We would design the cutoff frequency for the low pass filter using the equation that comes from the transformation. In this case, the F3 frequency is 0.35, the F4 frequency is 0.4, the F0, the center frequency of the band pass filter, is 0.25. So we would use a low pass filter prototype with a cutoff frequency of 0.125 and a transition width of 0.05. And again, these target values for attenuations for choosing our window function. Since these are the same attenuation requirements we had with the previous filter, we'll again find the Hanning window is the one that would be the choice here. We know its C value is 3.21. We could use that to choose the length then of this filter by dividing the 3.21 by now 0.05, and we need a much longer filter. In this case, a length of at least 64, so we'd have to round that up to an odd number 65 at least. And rather than going through all those values, here's the results. The low-pass prototype for a 65 length filter and its magnitude response are shown here. Again, seeing that we did in fact meet the 40 dB attenuation at 0.15, and we in fact did better than 1 dB up here at the passband edge. When we transform that to the bandpass filter by modulating all the sample values of the unit sample response by 2 cosine 2 pi n over 4, the bandpass filter's unit sample response values look like this, and we see the frequency response that we achieve there. And notice we did in fact achieve all of the specifications for the filter. Now, that's the typical way to use this technique. Again, because similar to many other filter design techniques, it's typical to start with a low-pass prototype filter and convert it to whatever one we wanted. In the case of windowing, though, we do have another option. We could design things starting with a low-pass prototype impulse response and using a spectral transformation like we've shown here to convert it to another type, which is typical of most design techniques. In the case of the windowing technique, though, we have the choice of actually starting with the ideal unit sample response for either a low pass or a high pass or a band pass or a band stop filter. So we could take an ideal unit sample response for the filter we actually want at the end and not do any transformation on it. Now, to do that, we need to derive what are those other ideal impulse responses. We said for the low-pass filter, the ideal impulse response, because its frequency response had a rectangular shape, the inverse transform, a Fourier transform of that was a sinc function. What about the high-pass filter? The high-pass filter looks kind of like, again, a flipped-over version, or well, probably flipped over would be the best way to describe it, and therefore its ideal unit sample response is again like a negative sinc function, so 1 minus, except the center sample now has a value of 1 minus 2fc, where 2fc was the center sample value of the sinc function for the low-pass filter. So this is sort of like applying that frequency transformation to the unit sample response ahead of time. If we were designing with this impulse response, then we would plug our desired F's cutoff frequency value for the high-pass filter directly into this formula. We would compute these unit sample response values, multiply them by a window function, and we would have the final unit sample response for a high-pass filter. For a bandpass filter, we would have this unit sample response. We have a pair of sinc functions where we find the difference between them. So you might think of this as having a big rectangular function in the frequency domain that has a one-sided width of fc2, and we're subtracting off another rectangle function, narrower one, with a cutoff of fc1. That's creating this unit sample response equation. An ideal band stop is again 1 minus that, so we flip things over, change the signs on all these, so the negative with the fc1 becomes a positive, the positive fc2 sign becomes a negative, and we subtract this 1 from the center value. And so again, the way we would use these is as the starting point for a band pass filter or a band stop filter. We would use these equations, depending on which filter we were trying to design, as our ideal unit sample response values. We'd multiply these by a window function, and then we would have our final filter. No transformation needed. Let's see how that would have worked. Let's compare doing our high-pass filter from the original example using a length 11 filter with our final cutoff frequency value that we determined. That was 0.305 with the handing window. The way we did that previously was starting with a low-pass filter impulse response, a sync function, multiplied it by a window function, the handing window function, to get the windowed low-pass filter, and then transforming that using the low-pass to high-pass transformation, and got these values for the unit sample response of the high-pass filter shown at the bottom here. And so this is what we got for our final filter design after the transformation. Alternatively, we could have started with a high-pass filter's impulse response, plugged in for all the appropriate values of n for these equations, and come up with these ideal high-pass filter impulse response values, multiply them by the same window function that we did before, and now we have a windowed high-pass filter unit sample response. And if you'll notice, these values are identical to the ones we got with the previous example, the previous process, as they should be. Just again, we're doing the transformation on the unit sample response at the beginning rather than doing it at the end. So we have these two options for how we can take forward this technique. So which one should you use? Well, that's up to you. You can do it either way, whichever one is easier for you, or just that if you're doing it with the advantage of doing it with the low pass prototype is you only have one unit sample response you have to know, the sync function. If you're going to start with the appropriate unit sample response for the shape of the filter you want, then you've got 4 different ones you need to keep handy. Okay, so that's the basic technique. Now as time has gone on and people have tried to improve the technique, there have been some little tricks of the trade that have come along that are worth knowing. First of all, we alluded to this in class, we'll notice that a lot of the window functions used in this technique, or in general, have 0 values at either end of the window function. And so when we use these kind of functions, then the windowed unit sample response of the filters we design with this technique will always have 0s at either end of the unit sample response. So in this case, while we say we have an 11 length filter, and there are actually 11 coefficient values, 2 of them are 0s, so there's really nothing to compute for those, and they really don't add any value to the filter. So we could just as well treat this as a 9 length filter and do only the actual 9 computations that we need in this difference equation and leave those off, saving hardware or software or computing time, and also having less group delay because we have effectively a shorter filter now. So an equivalent 9 length filter would have been making the minus 0.008 coefficient the B0 coefficient instead of the B1 coefficient, and so on, shifting them all down by 1 and leaving off the final one at the end. And we would see that other than the phase delay, these two filters would operate identically, would have the same magnitude response. Now you can actually do this design technique using MATLAB. MATLAB actually has its own command for FIR design using this windowing function. It's the FIR1 command, and returns the B coefficients, the unit sample response values for the filter, where the parameters are n, omega n, and window. It designs an n-order low-pass filter, so a filter that a length with a number of coefficients equal to n plus 1, and sets the gain of the filter at 0.5 or minus 6 dB at the frequency specified by omega n, Omega n is the cutoff frequency, but notice again this is using MATLAB's normalized radian digital frequency. And so compared to our cutoff frequency, we would say the omega n value would be twice the cutoff frequency when it's expressed in cycles per sample. That's because the omega values are 2 pi times the frequency, but MATLAB normalizes out the pi value, so you get 2 times FC. The window variable is a array or a vector that has to have the length of the final filter, so it has to have a length of n+1 or n+1 samples in it, and it should contain the sample values of the window function that you want to use for your design. If you leave off that parameter, the FIR1 command will use the default to the Hamming window. There are also different permutations shown here at the bottom. You can tell this function that you want a high pass filter or a band pass filter or a band stop filter by the way you specify the command, and so that's available to you as well. Now there are also 2 additional windows that get a lot of use in practice because they give you more flexibility than just our little table for how we do the trade-off between ripple amounts and transition widths. These are 2 window functions that actually have parameters in them, values that we can set and adjust to control that trade-off. And they trade off the window's main lobe width, which affects the resulting filter's transition bandwidth, and trades that off with the side lobe height, which leads to the maximum ripple amounts. These windows are the Kaiser window, which is very widely used and based on Bessel function computations, and the Dolf-Chebyshev window, which is an optimal window that provides the narrowest main lobe width that you can achieve for a given amount of maximum ripple. And it's based on Chebyshev polynomials. So here's the Kaiser window. The values for the Kaiser window, the W sub n values, are actually a ratio of 2 Bessel functions, where these are 0-order modified Bessel functions of the first kind, which if you're not familiar with them, that's okay. We would typically use tables or special computations to come up with them. They're defined by this particular equation for the Bessel function of the parameter alpha. Notice it has, in this case, we have a Bessel function with a parameter beta and another one with a parameter alpha, and they're related this way, where beta is the value we're manipulating to change the resulting shape of the window, and that trade-off between transition width and ripple amounts. Beta is related to alpha by this formula. And the idea behind the Kaiser window is it's designed to minimize the amount of energy that's outside the main lobe in the frequency domain. So the idea is we're minimizing the energy that would go into those side lobes so that they're as low as possible for a given main lobe width. And the alpha and the beta parameters determine the main lobe width. They're coupled. It's related to the percent of ripple. So as that alpha value goes up, so as alpha goes up from 0, 5 to 10, the main lobe width gets wider and wider and wider, but the side lobe height gets lower and lower and lower. So that's the trade-off. The higher alpha values give us lower side lobes, wider main lobes. If you set the value of alpha equal to 0 in a Kaiser window, you get performance comparable to a rectangular window in terms of main lobe width and side lobe height. If you set the value of alpha to around 8, you get a much wider window, much lower side lobes, comparable about to a Blackman window. But the beauty here is not what is it at these particular values, but the fact that you can choose any intermediate value for alpha in order to control that trade-off. So how do you use these windows? Well, there's some design equations that we use to come up with the Kaiser window and the alpha and beta values you need. Again, we start with the attenuation specs for the passband and stop bands. And we want to come up with a single parameter A, which is the worst case attenuation that's allowed. And then use that A value to compute the alpha parameter in the Kaiser window using one of these three equations depending on the value of A you're trying to achieve. If you're trying to get a lot of attenuation, then you're going to need to use this equation. For intermediate values of attenuation, we can use this better fit equation. And for fairly small values of attenuation needed, well, alpha equals 0, you're effectively using a rectangular window. Also need an equation to compute the filter length that we need, and again that's related to the attenuation we're trying to achieve. So for first we compute a k value based on the attenuation and its range, plug that k value into another function to compute the required window length, and again choose an odd value, rounding that up. So that's the ceiling function is doing for us. In MATLAB, once you know your m value you need and your alpha value you need, you just use the Kaiser window function with those two parameters, and it will give you m samples of the window with that alpha parameter. Dolf-Chebyshev window is a similar window that has an adjustable trade-off between the main lobe width and the side lobe height. It's based on a much more complicated formula of combined cosines and a parameter that's actually comes from Chebyshev polynomials. And in this case, the beta and gamma are two of the parameters in this computation. Gamma is the one that we use to control the trade-off. The conceptual design of a Dolf-Chebyshev window is that it's an optimal window that minimizes, in this case, the main lobe width for a given ripple percentage. So kind of the opposite of the Kaiser window. The value of gamma determines the percentage of the ripple by setting the window's side lobe height. So for example, for the gamma parameter, as the gamma goes down, the main lobe width gets wider and the ripple goes down. So you can think of the gamma parameter as being a linear version of the attenuation that you want to achieve. So for example, the gamma value of about 0.1, which is 10 to the minus 1, we get the equivalent of a rectangular window kind of performance, somewhere around minus 20 dB of attenuation in the worst case. Notice that, so for the same main lobe width as a rectangular window, the Dolf-Chebyshev does a little better in worst case attenuation and is flat, whereas the rectangular window rolls off a bit. So again, this is that optimization. The Dolf-Chebyshev windows trying to maintain the same value of attenuation at all frequencies for a given main lobe width. And actually, the other way around. I'm sorry, for this amount of attenuation, it's trying to give you the best you can, and give you then the best main lobe that you can achieve for that amount of attenuation. For a much smaller value of gamma, like 0.0001, that's sort of equivalent to a Blackman window. So again, achieving the same sort of main lobe width as a Blackman window, the Dolf-Chebyshev window has a much better worst case value for the attenuation. And how much attenuation you get, well, again, you can turn the gamma parameter into a dB value, and that's roughly where you'll end up in your attenuation. So gamma is like the maximum side lobe amplitude compared to the maximum main lobe amplitude. It's that ratio in linear terms, not dB terms, or a percent ripple. Now, how do you use these? Well, again, now you're going to work with ripple parameters rather than attenuations, and we find which is the worst case, which of the passband or stop band ripples that's allowed is smaller, and choose the smaller one of those. Calculate the gamma parameter from that as minus 20 log of that minimum amount of ripple that's permitted. And then calculate the filter length from the chart using actually the side lobe level, the gamma level in these equations or with MATLAB that's given in dB, not in linear units. And we would use the ChebWin command with the M parameter and the gamma parameter. Here's a chart showing how the Dolf-Chebyshev window with different values of gamma fit in the context of other standard windows like the Hanning window and Hamming window. So again, with a parameter of gamma around 20 dB, the Dolf-Chebyshev window performs similarly to a rectangular window. At 40 dB, it's actually achieving a little better than that in side lobe attenuation, and it's fitting between the Hanning window and the Hamming window. By using 50 dB or 60 dB for the gamma parameter, we can get attenuations between the Hamming window and the Blackman window, so we can more finely tune things here in these realms if we don't want to make the jump all the way to a Blackman window, and get a shorter length filter with the Dolf-Chebyshev than we could with Blackman. And so that's the end of the story on the FIR filter design by windowing. It's actually a fairly straightforward technique. We've gone through a lot of detail about the technique and how it works, and hopefully it's understandable to you. Next week in the laboratory, we'll put that to work, and you have some homework problems too that you can work on how to see how the technique works and see it in action. So hopefully by sorting through those, the steps and how to actually execute them will become clear, and you'll see it's actually a fairly straightforward technique. So we'll see you back in class on Monday. Hope you have a good weekend, and hope you've enjoyed this video.